Hey guys, and welcome back to my channel. In this video, we'll be discussing the Boltzmann distribution. So you might be asking, why are we talking about the Boltzmann distribution? Aren't distributions usually covered in more statistical mechanics or thermodynamics parts of chemistry? And yes, they usually are, but the Boltzmann distribution specifically has a lot to do with discrete energy levels. And in the past videos, we've been talking about how atoms and electrons in atoms have discrete electronic energy levels. They can't just be any energy. There's these sort of quantized energy levels that are sort of discrete. And so we can use this Boltzmann distribution in relation to atoms like the hydrogen atom and analyze the hydrogen atom using the Boltzmann distribution. So what is the Boltzmann distribution? Basically, it's asking the question, in a certain system, what is the probability that I find the system at a specific energy state? So one of the main examples we'll be discussing is what is the probability that I find a hydrogen atom in the first excited state or the second excited state or one of the excited states versus the ground state. So let's just get right into it. Okay, so again, the Boltzmann distribution is used for systems with discrete energy levels. This is really important. Discrete energy levels. And a good example is the hydrogen atom. So if a system is in thermal equilibrium with a temperature T, that means if the system all has the same temperature, it's been around long enough so that the entire system is at the same temperature in thermal equilibrium, then the probability of state S, given that that state has an energy E sub S, is given by this equation here that's written down below. Now this looks a little complicated, but I'm going to sort of break it down for you. So the probability of the state S is equal to 1 over Z. This 1 over Z term is basically a normalization factor. It's not super important, and I'll talk about it a little bit later. Times the degeneracy function. That degeneracy function, d parentheses E sub S, is the number of degeneracies of that energy state. So for example, say there's an energy state of 10 joules, but there's like 3 of those energy states. There's 3 possible states that have that energy of 10 joules. Then it should be 3 times more likely to happen because that state has 3 different, there's 3 different possibilities for us to be at that energy state. So that's basically why we have a degeneracy factor included. Next, we multiply by what's called our Boltzmann factor, and this is the really important part of the expression, right? Our e to the negative b e sub s. So what is this beta term? This beta term is 1 over kBt, where kb is the Boltzmann constant and T is the temperature of our system. E sub s is the energy of the state. So this should sort of make sense, right? The higher energy of the state, the lower the probability will be because this is a negative exponential function. Now let's talk about what our z term is, right? Our 1 over z. Z is called the partition function, and this is a common terminology you might hear. The partition function is just a normalization factor, and all this does is make sure that the sum of all the probabilities across all the different energy states is equal to 1, because that's how a probability is defined. The sum of all the probabilities must be equal to 1. And let's talk about degeneracies a little bit, because we talked about degeneracies in the previous video, but I want to talk about, refresh you on it, because in the problem that we'll be doing, we'll be using the fact that the hydrogen atom has some degeneracies in its first excited state. So in an a hydrogen atom, only one orbital with energy E1, there is only one orbital, right? That's our 1s orbital. But there's 4 orbitals with energy E2, our n equals 2, right? Because we have our 2s orbitals and we have our 3 2p orbitals. And this is something we talked about in the previous video, but I just wanted to refresh you on that. Okay. So what is the sort of useful analysis of the Boltzmann distribution that you generally use, right? We want to take ratios because ratios are pretty useful, and what we can do with the ratios is we can get rid of our partition function, and we can take the partition function out of the analysis because that's sort of a normalization factor. But if we divide these, and take a ratio, we can just cancel this out. So basically the question we're trying to ask now is, if I have two energy states, how much more likely will my system be in one versus the other? So if I take the probability of S2, so that's my second energy state, or my second state, divided by the probability of S1, which is my first state, then just by substituting in the Boltzmann distribution expressions, which is written right there, right? You can see that our 1 over z factors cancel out, and we're left with the ratio of the degeneracies of the state times e to the negative beta delta E, where our delta E is the difference in our energies between the two energy states. So this is a really nice expression because we've just gotten rid of our partition function and we don't have to worry about trying to calculate that. We only have to worry about our degeneracies and our temperature, which is included in the beta term, and the two energies of the two states, and we can just take the difference of those two. So on this slide, I'm going to try and give you a little bit of intuition for the Boltzmann factor and the Boltzmann expression. First, we're going to take a chemical reaction, A goes to A star. Okay, this is just like any normal chemical reaction, and we can treat it like any normal chemical reaction. But A and A star are just the same system at different energy states. So for example, we can think of A as a hydrogen atom in its ground state, and A star as the hydrogen atom in its first excited state. So from AB Chem, we know that delta G of this reaction, the free energy change, is equal to negative RT ln K. This is probably an equation you had to memorize. But this equation gives delta G in joules per mole. Say we want a delta G in joules per atom. So what we're going to do, if we want delta G in joules per atom rather than joules per mole, we got to divide this expression by Avogadro's number, right? So let's do that. So now we have delta G in joules per atom is equal to negative KB T ln K. Where did we get the Boltzmann constant? Where did we get KB? KB is just our R divided by Avogadro's number. So this is why we can just substitute in KB into this expression. Now we can sort of think of delta G as similar to our delta E, right? Our delta E in the Boltzmann expression is the difference in energies of the two states. The delta G of this chemical reaction is just the change in free energy, the difference in free energy of the two states. So they're really similar. So what we can do is we can replace our delta G by delta E. Now we have delta E equals negative kBT ln of K, but our K of this chemical reaction is the concentration of A star divided by the concentration of A, products over reactants. So we can substitute that in. Now if we move this around, right, and solve for A star divided by A, we get concentration of A star divided by concentration A equals e to the negative delta E divided by kBT. We can also think of concentration A star over concentration A as sort of like the probability of A star divided by the probability of A. If A star is much, say the concentration of A star is much greater than A, that also implies that the probability that the state is in this energy state of A star is much higher than the probability that it's in A, or vice versa. So this equivalence sort of makes sense. But this e to the negative delta E over kBT is the exact same thing as the Boltzmann factor. So hopefully this gives you a little bit of intuition, and this gives you a way to think about it such that it's not so abstract and just a formula, another formula you have to memorize. So now we're going to go over a Boltzmann factor problem that should give you a sense of how we can use the Boltzmann factor in an actual problem that could come up. So the question is, what is the ratio of hydrogen atoms in the first excited state to the ground state on the surface of the sun, given that the ionization energy of hydrogen is 13.6 electron volts and the temperature of the sun is 5800 Kelvin? So what exactly is this asking us? This is asking us the ratio of excited state atoms to ground state atoms, which is basically equal to the probability that an atom is in the excited state divided by the probability it's in its ground state. And this looks very, very much like a Boltzmann factor question, right? When we have the ratio of these sort of probabilities when we have discrete energy levels. So let's use the Boltzmann expression and figure out what this should be, right? So in the Boltzmann expression, we have the degeneracy factors of H star divided by the degeneracy factor of H times e to the negative delta E divided by kBt. So what exactly do we need to figure out in order to solve this question, right? We don't know the degeneracies yet. We need to figure out the degeneracies. But we know what kB is. That's just a constant. That's the Boltzmann constant. We also know the temperature, which is given in the problem, 5800 Kelvin. But we don't know the energies, right? We know that the ionization energy is 13.6 electron volts, but we don't know the energies of the ground state and the first excited state. So let's sort of figure that out first. First, we want to figure out what E2 and E1 is, right? This is what our delta E is. Let's look at what the hydrogen atom looks like, right? We have these sort of different shells around the nucleus. And we know that ionization energy is defined as the amount of energy it takes for me to take an electron from the ground state and remove it all the way to n equals infinity. And at n equals infinity, my energy of that electron, the potential energy, is 0. Because there's no sort of attraction between the electron that far away and the nucleus of the atom. So basically this is telling me that to get to E equals 0, which is all the way out in ionization, I need to apply 13.6 electron volts. So that means that my ground state is at negative 13.6 electron volts. Because it takes 13.6 electron volts for me to get to an energy state of 0. So good, now we found what E1 is, right? But how do we find what E2 is? This is where we need to think back to a previous lecture when we discussed that the energies, En, is proportional to 1 divided by n squared. It goes down by n squared. So let's use that with our 13.6 electron volts. So we know that our first state has n equals 1 and has an energy level of negative 13.6 electron volts. That means our second state, because it's proportional to 1 over n squared, you must have to divide our negative 13.6 by 4, because we need to divide by 2 squared. This means that our second energy level has an energy of negative 13.6 divided by 4, which is negative 3.4 electron volts. Okay, cool. Now we can find the change in energy. We can find the delta E. So this gives that our delta E is negative 3.4 minus 13.6, or minus negative 13.6, which gives us 10.2 electron volts. Good. So now we just need to find the degeneracies, or the ratio of the degeneracies. So let's look at our ground state first. With our ground state, we just have our 1s orbital, right? Our electron can only occupy the 1s orbital. So there's only really one degeneracy, right? We can only have the electron be in the 1s orbital. Whereas with our n equals 2 state, our first excited state, we not only have the 2s orbital that the electron can occupy, but we have the 2px, 2py, and our 2pz, right? All three of our 2p orbitals that have the same energy as our 2s orbitals. So we have 4 degenerate orbitals. There's 4 orbitals with the same energy, so we have 4 degeneracies. So now we're able to plug these numbers into our expression and figure out what the actual ratio is. So probability of H star divided by probability of H is the ratio of our degeneracies, which is 4 divided by 1, e to the negative 10.2 electron volts divided by kB times our T, which is 5800 Kelvin. And you can plug this into your calculator if you want, but once you plug this in, you should get something like 5.5 times 10 to the negative 9, which you can also represent as 5.5 divided by 10 to the 9. And this should sort of, basically tells you that for every 10 billion ground state hydrogen atoms, for every billion ground state hydrogen atoms, we have around 5 excited hydrogen atoms at the surface of the sun. So hopefully this gave you an example of how the Boltzmann factor can actually be used to calculate something pretty relevant, like the ratio of hydrogen atoms in the excited state versus the ground state on the sun. I hope this video was informative, and I hope you'll stick around for my other videos. Thank you, and I'll see you guys in the next one.